Okay, hello guys. This platform is made to help students understand math and physics. Mainly, I'm talking about secondary students, but I'm starting now with grade 12 because they have official exams soon. I hope these videos are beneficial as much as possible, and I hope you share, like, and subscribe for new videos. I'm starting here with the capacitor chapter for 12 LS, and I will start solving the official exams from the easiest to the hardest. So you can find the video that fits your level and you can continue on watching so you can 100% understand the chapter. Now, before I start, I have to explain briefly the things that I need from this chapter. And the notes that I will give here, they are not the information you're supposed to know. So don't give up your courses. Of course, you can take the notes as part of the summary, but you have to know in details the chapter. So you have to read your courses with the teacher again. Now, what you have to know that in this chapter we have two main formulas. The first one is I equals dq over dt, but sometimes we put it plus dq over dt, sometimes minus. The positive sign is for when we're charging a capacitor, and the negative sign is when we're discharging a capacitor. And why is that? Because we always take the current is going in the positive direction chosen in the exercise. So I is always positive for us to make things simpler. Okay. Now, when the capacitor is charging, the charge around the capacitor is increasing. So Q is increasing. Now, this is the capacitor. This is the current flowing through the capacitor. This is the positively charged one, and this is the negatively charged one. With time, the capacitor is progressively increasing. So the charge that are accumulating on the plates, they are progressively increasing. So Q is progressively increasing. Now, every time we have an increasing function or variable, its derivative should be positive. Okay? Now, since I is positive in the phase of charge and dq over dt is also positive, I can simply say they are equal. But in the phase of discharge, But in the phase of discharge, Q is decreasing because the accumulated charges on the plate, they are going out, flowing into the circuit. Okay, so the charges on the plates, they are progressively decreasing, and every decreasing variable or function, its derivative is negative. Now, I cannot say that I is positive and dq over dt is negative. That is a false equality. So I'm supposed to write a minus before dq over dt, so I can simply make the whole function positive again. This is for the phase of discharging. Okay, so the first main formula is I equals dq over dt plus or minus, but I will simply take now the positive side of things. The second main formula in this chapter is q equals cuc. What do I mean by that? The charges accumulated on the plate, they are dependent on the capacitance of the capacitor, how much it's capable to hold charges on the plate, and you see the voltage of the capacitor. Okay, now since the capacitor progressively charges, so Q is a variable quantity during the charging phase or the discharging phase, and same for the voltage, they are changing. The only thing in this formula that is constant over time is the capacitance. It's a constant value. Why? Because simply the capacitance doesn't change unless you change the dimensions of the plate. For example, you have a plate that has a thickness T and a height H, let's say. Okay, and I increase the plate. I will make it slightly more bigger or smaller. Then this will affect the capacitance. Or simply, if I change the distance between the plates, if I have the plates separated by this much, okay, and I separate them from each other by this much, of course, then the capacitance will also change. But we're keeping things simple here by keeping everything constant. So the capacitance will be constant. Okay, why am I saying that? because I have a formula here for Q, and I have it here also in the second formula, also Q. Are they related to each other? They can be, yes. If I equals dq over dt, and this is really, really important, I can simply replace Q here and Q here. So what do I get by that? I will get I equals d over dt. I didn't touch that, so it stays the same. Q is changing now. I'm replacing Q by its formula, which is CUC. Okay, so I will get the derivative of CUC. And since we just said that C is constant over time, so I will keep it outside the derivative, as simple as that. And I will keep UC inside the derivative because it's the variable quantity here. Okay, so we get the third formula, which is very needed for the differential equation that we will be solving in the problem. Okay, as the third most important formula of this chapter. Okay. Now, in case you struggle with the units, I is in amperes, P is in farad, and by the way, the capacitance should have a very small value, like 0.1 farad maximum. Okay, if it's more than that, if it's more than 1 or 2, this is what we call superconductor. So we prefer to have small numbers for the capacitance. Okay, U is the voltage, obviously volts. What do we have to? We have Q. Q, it's the charge in coulombs. And that's it mainly for now. Okay. Now, in electricity, we have the three main variables, which are the charge Q, the current I, and the voltage UC. Every time they ask you to find the differential equation for Q, you should have in your differential equation only Q. So you have to replace I or UC if you have one of these in your equations. Okay, so the exercise is about Q or I or UC. You cannot have those three in the same equation. Okay. And the last thing I have to talk about is tau. Tau, it is not any time. It's a special time. It's equal to R times C. R, it's the resistance in the circuit, which is expressed in ohms, and coulombs, farad. And tau is simply the time in seconds. Why is tau a special time? Because every time I find the 63%, this is the charging phase. If I have the maximum value, it's 8 volts. Every time I try to find the 63% of the maximum value, which is 8 here in my case, I go out to the curve so I can find the time. It turns out that the time is always being RC. So it's a special time. That's why we call it tau, and that's why it has its own formula. Mainly, we don't use it as a formula. They ask us to prove it, and then we can use it. Okay, so what is the definition of tau? Tau, it is the time. They sometimes ask about the definition, so it's really important. It is the time that represents the value where it achieves 63% of its maximum. I took example U, the voltage, okay? But simply we can have a curve for Q. Q in function of time. We can have one here, maximum Q. Okay, Q max. So it's also 63% of the Q max. So I didn't simply just say the voltage. It achieves the 63% of the maximum voltage. I said the maximum value, okay, because it can be voltage or charge. Now, what about the phase of discharge? In the phase of discharge, every time I try to find, let's say this is 8 volts, it's the voltage and function of time. Every time we try to find the 37% of the maximum value on the curve and we go out to find the time, This is also tau, which is RC. So it's the same sentence, I just rewrite it, but instead saying 63%, we say 37%. Okay? So this is in the phase of charge. And rewrite the same sentence, but instead of 63, we say 37. This is the phase of discharge. Okay? These are the main ideas of the chapter. Now, let's start solving the first session for LS 2022. This is the third exercise, and I will continue on solving the capacitor in the series. So you can 100% complete this chapter, and you can consider yourself that you practiced enough. What do we have here? We have this circuit. It is made out of a switch, K, a generator or a battery, a capacitor, and a lamp. Okay. The aim of this exercise is to study the brightness of a lamp in two experiments. For this purpose, consider an ideal battery of electromotive force E. Now, the formula of the battery, voltage of the battery, is not simply just E. It's E minus Ri, with the R being the internal resistance of the battery. Okay, so in reality, we have internal resistance for the battery. Okay, but simply in this chapter, and mainly they always consider that the battery is ideal, as they said here, or it doesn't have internal resistance, so we neglect this part here. Okay, but keep it in mind. What if they don't neglect it? Now, a lamp L acting as a resistor of resistance R. So the lamp here is a resistor. A capacitor of capacitance C. Okay. Now, the first experiment, we're charging the capacitor. So mainly it was initially uncharged. So you'll see at the beginning of the experiment, when the time was 0, it was 0 volts. It wasn't charged. Now, in series with the lamp and switch K across the battery. Switch K is closed. It's closed, so now we have a current. Show that the differential equation that governs the variation of the voltage. Okay. Every time you read this question and they ask about the differential equation, you can decompose this into two steps or three sometimes. The first step, you have to write the law of addition of voltages for the circuit that you have, which is U of the battery. The battery is giving out to the lamp and the capacitor. Okay? Now, since the lamp is considered a resistor, we all know that every time we have a resistor, voltage of a resistor, we can replace it by Ri. And U of the battery, now we said that the battery is ideal, so it's E minus Ri. And since it's ideal, we can remove this part, so it's only E. Now, the first question that pops up to a student's mind is, why don't we replace UC too? Because they want the differential equation here to be in function of UC. So I'm not supposed to replace UC. Okay? So U of the battery is E, UL, which is the resistor Ri, plus UC. Now, the first thing that I said before is you're supposed to have a Q, or I, or UC. You cannot have two variables in the same differential equation. So since we're choosing UC now, we have to replace I by something. I cannot have I and UC at the same time. So on the side, I will say that I know about I that it's dq over dt. dq over dt, and I know that Q is C, UC. And since C is a constant, we can keep it outside the derivative, and we get this new formula. So now I, it is replaced by C duc over dt. So the value of I here is the same as I here. So we can simply replace it by C duc over dt. You can ask me, why didn't you just replace I by dq over dt, the main formula that we know? You're right. But then I will get to the same problem, which is having Q and UC, which are two different variables in the same differential equation, and this is not what I want. So the first step is writing the addition of voltages, and this is the second step here, replacing I by its formula, the most important formula for the differential equation. Now, I told you that we can have a third step, but they didn't ask for it here in the question, which is keep the derivative by itself. duc over dt don't have any quantity next to it. Here we have RC next to duc over dt. If I want to get rid of this, I have to divide the whole thing by RC. I divide by what's next to the derivative. Next to the derivative duc over dt, we have RC, so we divide by that. What do we get? We get E over RC. RC over RC duc over dt, simply we remove RC from the numerator and the denominator, and here we get UC over RC. But since they didn't ask for the third step here, I can keep it out, okay? But it's really important, mainly they asked about it. Now, the second question, the solution obtained. Now the differential equation, it's like a second degree equation. Second degree equation, it has two solutions. Same for the differential equation, it has a solution. And this solution is you see E, 1 minus E minus T over tau. Determine the expression of tau in terms of R and C. This is also a very repetitive question, and it is very important. And you can get from these two questions, by the way, at least 2.5 points, just because you memorize the steps that you have to follow. Now, let me break that down in few steps. 1.2, I have the solution, E, 1 minus E minus T over tau. Every time they ask you to find tau, do these steps. The first one, if you find the derivative in parentheses hard, you can expand first. So the first step, expand the solution that you have. And keep in mind what's constant and what's not. E is a constant value, it's 9. They said that at the beginning of the exercise here. Okay, so E is a constant. Okay, and the exponential, definitely it's not a constant because the exponent is t and the time is changing. Okay, so it's the variable here. Now, the second step you have to do is find the derivative, duc over dt. The derivative of a constant, the derivative of E would be 0, it's a constant. Now, the derivative of this term here, you tell me E is the same as E we just talked about, so it's 0? Of course not, because E is multiplied by the variable. So if the constant is multiplied by the variable, we cannot simply remove it. So I will keep minus E. Okay, now I have to find the derivative of the exponential. Now, you are mainly familiar with the exponential in math. Every time you have EAX, you take A and you put it on the line next to E. Except here, I don't have X. In physics, we have T. The time is my variable here. Okay, so minus E, and I will rewrite the same exponential, and I will put a parentheses in between if you really struggle with math. This is my step-by-step way of solving things. Okay, and what is next to the variable T here? Next to the variable T, we have minus and we have tau. So simply I take them and I place them between the parentheses. And of course, I cannot leave the numerator empty, so I have to put 1. Okay, why didn't I put T on the line? Because T is the variable. We don't change the place of the variable. We just change the place of the constant next to it. Now I multiply them. Minus and minus would simply be plus. And E times 1 over tau, it would be E over tau. Now, you did the first two steps. You expanded the solution, great. And we found the derivative of the solution, also great. The third step, you rewrite the differential equation above. This one here. RC duc over dt plus UC. Now, your variable, which is the voltage, you have to replace it of what you just did in the first two steps. So you see it's replaced by this, and VC over dt, it is replaced by this. What do we get? E RC. Now, I have a thing in math, if you really struggle with math, every time you replace something by another expression, just put this expression between parentheses. It would feel easier. So instead of duc over dt, I will put e over tau, e minus t over tau, plus, plus, uc, it's e minus e minus t over tau. Okay? Now, the fourth step, they're really easy if you practice on them and you take them in steps, because sometimes the students forget the steps and they really confuse on how to solve it. Now, the fourth step, take e minus t over tau as a common factor. Now, the numbers or the terms that have e is this one and this one. The only one without exponential is this one here. Okay, now I will rewrite everything and I will take exponential as a common factor. What do I have? So the first term, it has exponential, we remove it. We still have RCE over tau. We're done with the first. The second, plus E, we said plus E, it doesn't have any exponential, so we will keep it on the side outside the parentheses. And the last term, it has minus E. Okay? Sorry, I put a parenthesis. Okay, and the last step you have to do, the fifth step, you take the factor of the exponential equals to 0. This one, the exponential can never be 0, and e is obviously equal to e. The last thing that we don't know anything about is the factor in parentheses, so we take it equal to 0, RCE over tau minus e equals to 0. So RC over E tau equals E. I took E to the other side. It will become plus E. Then E and E, we remove them. We will end up having RC over tau equals 1. Now cross multiply, you will get tau equals RC, and it should always be RC. Okay, so I know my answer is correct. Now, we finished 1.2.1. Now 1.2.2, calculate tau. Tau simply it's RC now. And the R in the given, in the third line, it's 10. And C, it's 0.1. So 10 times 0.1, it's simply 1 second. We calculated tau. Now 1.3, deduce that the expression of the charge current is I equals 0.9 E minus T SI. Okay. Everything I can think of is that I have the current I here, and I cannot deduce a solution by myself. So I have to relate it to something else that I know about. The solution that I know is the voltage. Is there any way so I can relate the current and the voltage? Yes. It's C duc over dt. So simply I say duc over dt. Do I know it? Yes, from the previous questions. duc over dt, it's here. This value here. And just replace it by its value. So I is equal to C, and it's E over tau, E minus T over tau. Now, I replace what I know. The capacitance is 0.1. The ideal voltage, the electromotive force is 9 over tau, which is 1, E minus T over tau, which is 1. What do I get at the end? I will get that I is 0.9 E minus T, and this is what they want. Okay? That's really easy if you can just relate the questions to each other. Okay? Now, The second part of this problem, now we're discharging the capacitor. Okay, now the capacitor is charged on the positive side of the plate. Okay, and it will give out a new current in the opposite direction. Now we close K at T0 equals 0, we reset the clock and we start a new experiment where we're discharging the capacitor. The capacitor discharges through the lamp. Okay, now we can see on the graph that the voltage of the capacitor, it is progressively discharging. Now use document 6 to determine the value of the time constant tau prime of this RC circuit. Okay, now 2.1, every time they ask you about tau graphically, it has three main ways. The first one is theoretical, like we did in question 1. We solve the differential equation and we get tau, okay, using the differential equation. We use the differential equation, we do the 5 steps that I told you about, and you will get that tau equals RC, and we calculate tau. The second way, it's graphical. The second and the third way, they are graphical. The second way, we know that at tau, UC should be 63% if it's charging, but now we're discharging, so it's 37% of the max value. And this is really preferable. Okay, then we can use the graph so we can find where tau is. This is what I will do here. The third way, and it is also a graphical way, they draw the tangent for us at t0 equals 0. Usually, they draw the tangent here. Let me use my ruler. They draw it mainly like this. And they ask you to find tau graphically. You tell them the point of intersection between the tangent at time t0 equals 0 and the x-axis, the time axis, it's 1. So this is tau. But if they don't draw the tangent for you, preferably you don't use it. You use the second method. Okay? So tangent at t0 equals 0, then we find the intersection with the time axis. And they are both graphical methods. The second one is better, honestly. Now, what do? I find the voltage, the 37% of the max value. What is the max value on the curve? The curve, it started from 9, so this is the maximum value. 30%, 37% of 9 volts, it's like saying 37 over 100 times 9. And it actually is, it will be 3.6, 3.7, something like that. 3.5, let me check the answer. Yeah, 3.3. 3.3. Okay. So it's 3.3, 3 volts. I go to my curve and I find where 3 is. This is supposed to be 3.3. And I find where the projection of this point on the curve is. It's 1. So tau is supposed to be 1. So once we find UC, we say using the graph, the time constant tau is supposed to be 1 second. Okay, now tau doesn't really change. Let me say something. Tau doesn't really change if we're not changing R or C. And since R is still the same, it remains the same. And same for the capacitance C. We didn't change the capacitor or its shape or form. So C is the same, and the resistance in the circuit is still the same. So why would tau changes, even if we're discharging? The formula says that tau depends on R and C. Now, the second part, given that you C equals E minus T over tau prime. deduce the expression of the discharge current as a function of time. Now they want us to find a new current, and they gave us a new solution, which is E minus T over tau prime. So this is actually tau prime here. Okay? And they want us to find I, like we just did in the previous part. Now, to relate I and U, we know that I is equal to C dUc over dt. But since here we're discharging the capacitor, we put minus. Because I is positive, it's going in the positive flow, as they said in the given. And C dUc is negative, so we put a negative sign, so to keep everything positive again. Now, what is the derivative of UC in this case? As I said before, we rewrite everything the same, and we put parentheses in the middle, and we just put the variable, the numbers next to t on the line next to the exponential. So we have the minus and tau prime, so it's minus over tau prime, and we put 1 to not keep the numerator empty. Now what do we get here? Minus e over tau prime, e minus t over tau prime, which is tau prime is 1, so we can simply replace it by 1. But I will keep it to the end. Now, what do I get for I? Minus c. duc over dt is what I just got now. So it is minus e over tau prime e minus t over tau prime. Okay, minus times minus, they will be removed. Plus c e over tau prime e minus t over tau prime. C is 0.1 by the given. E is 9. Tau prime is 1. E minus t over 1. Simply, I will also get the same current minus T. Why the same current? Is the current in the face of charge and discharge the same? Yes. Because if we're charging the capacitor, it will get to a point where it will behave as an open switch. The capacitor, when it's full, it will be blocked. It will block the current from flowing, so it's actually decreasing. And when the capacitor is giving out a current, it will also get to a point where it will be empty again, so it will not be able on giving out current. Then the current is also decreasing in the phase of discharge. Okay, so the current is always decreasing in charge and discharge of the capacitor. Now, the last question, conclusion. Using parts 1.3 and 2.2, so it's the question for the current in the phase of charge and discharge. Describe the brightness of the lamp in the first and the second experiments during the time interval 0.5. Justify your answer. 3. In both cases, the current I is decreasing. How did I know? Because in both cases, I got this expression. And E minus T, e to the power something negative. Every time the time increases, the exponential will be going towards 0, right? Because if the time is getting huge, e to the power minus something huge, it will approach 0, okay? So in both cases, the current is decreasing. So the brightness of the lamp is also decreasing. As simple as that. Okay? And after the time t, 5 tau, after we get to the permanent phase, in both cases, the lamp will be turned off. That's why mainly we use the AC currents for the capacitor to not completely charge it and make it block the circuit. Then I wouldn't get to my point in electronics and physics. Now, this is my first video. I hope you enjoyed it and share it if you find it beneficial. I'm also adding few information every time I solve some question. I hope they are beneficial too. If you need some help with specific chapters before the official exam, you can comment below. And that's it for me. I will post a new video soon. Thank you for watching.